distinct yet complementary trajectories. DNA computing, DNA computing, DNA computing, DNA computing, the most mature modality. The biocomputing revolution, a comprehensive analysis of DNA, organoid, and protein-based computational paradigms. Executive summary: the field of computing is on the cusp of a paradigm shift, moving beyond the established domains of silicon and quantum mechanics to embrace the intricate and powerful machinery of life itself. Biological computing, or biocomputing, represents a diverse and rapidly advancing frontier of science and technology that harnesses biologically derived molecules and systems, such as DNA, proteins, and living neurons, to perform computational tasks. This report provides an exhaustive, expert-level analysis of the latest research in biocomputing, focusing on its three primary modalities: DNA computing, organoid intelligence, OI, and protein-based circuits. It synthesizes foundational principles, recent breakthroughs, comparative performance, key challenges, the global ecosystem of players, and the profound ethical dimensions of this transformative field. The central thesis of this report is that biocomputing is not emerging as a monolithic replacement for classical computers. Instead, it comprises a portfolio of specialized computational paradigms, each uniquely suited to solve problems that are intractable for conventional machines. The motivations driving this revolution are clear and compelling. The potential for massive parallelism inherent in molecular systems, the extraordinary energy efficiency of biological processes, and the unparalleled data density offered by molecules like DNA. These advantages position biocomputing to address some of the most significant challenges of the 21st century, including the unsustainable energy consumption of artificial intelligence, the exponential growth of global data, and the need for more sophisticated, personalized medical interventions. This analysis reveals a field that is bifurcating into distinct yet complementary trajectories. DNA computing, the most mature modality, is evolving along two paths: computation for storage, leveraging its phenomenal density and durability for long-term data archiving, and computation for sensing, using sophisticated molecular circuits and nanopore technology to create revolutionary diagnostics for diseases like cancer. Organoid intelligence, the most futuristic and ethically complex frontier, utilizes lab-grown human brain organoids as a computational substrate. Its immediate impact lies not in building general-purpose computers but in creating unprecedented intelligence in dish models for studying neurodegenerative diseases and accelerating drug discovery. Protein-based circuits, operating at the intersection of synthetic biology and medicine, use the fast and dynamic interactions of proteins to create smart programmable cells. This modality is pioneering the concept of a circuit as medicine, where engineered cells can sense disease states and execute therapeutic responses from within the body. However, the path forward is fraught with significant challenges that are unique to each modality. DNA computing must overcome the high cost and error rates of synthesis and sequencing. Organoid intelligence faces fundamental biological hurdles in maintaining the stability and viability of complex living tissue ex vivo. Protein circuits must solve the immense design complexity of creating large, reliable circuits that function within the noisy environment of a cell. The global ecosystem driving this research is a vibrant network of pioneering academic institutions, such as Johns Hopkins University for OI and Caltech for protein circuits, and a burgeoning commercial landscape. This market is characterized by a foundational layer of picks and shovels, companies providing essential tools like DNA synthesis and sequencing, which supports a dynamic but more speculative layer of startups building specific biocomputing applications. Finally, this report confronts the profound ethical questions that biocomputing raises. These challenges are not uniform. They range from data security and DNA computing to biosecurity concerns with protein circuits and, most acutely, to questions of consciousness and moral status in organoid intelligence. Navigating this complex ethical terrain will be as critical to the future of the field as any technical breakthrough. The ultimate trajectory of biocomputing points toward a future of hybrid biodigital systems, where the deterministic power of silicon is augmented by the adaptive, low-energy, and massively parallel capabilities of biological hardware. This convergence does not just promise better computers, it promises to fundamentally expand our definition of computation and grant us the ability to program the universal language of life itself. 1. The emergence of biological computation. A paradigm shift from silicon. For over half a century, the concept of computation has been inextricably linked to silicon-based electronics. The transistor, the microprocessor, and the von Neumann architecture have defined the digital age. Yet, as the physical limits of silicon scaling approach and the energy demands of computation, particularly in artificial intelligence, become unsustainable, researchers are turning to a radically different and far older computational substrate: biology. Biological computing is an interdisciplinary science that seeks to use the components of life to perform computational tasks, representing a fundamental shift in how information is processed, stored, and manipulated. This section defines the foundational concepts of this emerging paradigm, explores the compelling rationale driving its development, and situates it within the broader landscape of classical and quantum computing. 1.1. Defining the field. From self-assembling molecules to living neurons at its core, a biocomputer is a computing device that utilizes components of biological origin, such as molecules of DNA and proteins, or even entire living cells like neurons, instead of silicon-based electrical components to perform calculations. The concept, though sounding futuristic, has historical roots, with the term biocomputer first appearing in literature as early as 1952, and theoretical proposals emerging in the mid-20th century as scientists began to decipher the informational nature of the genetic code. However, it is the recent, convergent advances in synthetic biology, nanotechnology, and microfluidics that have transformed biocomputing from a theoretical curiosity into a field of active and practical research. The fundamental mechanism of a biocomputer involves the engineering of a biological system, be it a collection of molecules in a test tube or a network of cells in a culture, to behave in a predictable manner based on a set of initial conditions, or inputs. The resulting state, product, or signal of the system is then interpreted as the computational output. This process can manifest in several distinct forms, traditionally categorized as biochemical computers. These systems use the intricate feedback loops and reaction cascades characteristic of metabolic pathways. The output is typically the presence or concentration of a specific chemical product, which serves as a signal. For example, a circuit could be designed where the presence of input molecules A and B leads to the production of output molecule C. representing a biological and gate biomechanical computers, similar to biochemical computers in their input-driven nature. These systems differ in their output signal. Instead of a chemical concentration, the output is the specific three-dimensional mechanical shape or conformation of a molecule or molecular complex. The computation is read by detecting this physical structure via electronic computers. In this modality, the output is an electrical property, such as the conductivity of a specially designed network of biomolecules. The system is engineered such that the electrical output changes in a predictable way based on the molecular inputs. While these classical definitions are useful, the modern field is more commonly understood through its primary technological modalities, which form the structure of this report. DNA computing, which uses the informational properties of nucleic acids. Protein-based computing, which leverages the functional diversity of proteins. And cellular or organoid computing, which utilizes the complex, emergent behavior of living cells and tissues. This diversification of computational substrates forces a re-evaluation of the very definition of computation. The field moves beyond the abstract, symbolic manipulation of a Turing machine, to a more physical, embodied concept. Computation is revealed not as something exclusive to electronics, but as a fundamental property of organized matter that can reliably transform a given input into a desired output. This perspective suggests that the rules governing biological systems are a form of natural algorithm, and that progress in biocomputing is as much a theoretical challenge in understanding these new computational models as it is an engineering one. We must learn to think in terms of molecular interactions and emergent network dynamics, a language far removed from the deterministic logic of a central processing unit. 1.2. The rationale for biocomputing: harnessing parallelism, efficiency, and density. The pursuit of biocomputing is not merely an academic exercise. It is driven by the recognition that biological systems possess inherent properties that offer profound advantages over silicon for certain classes of problems. These advantages, honed by billions of years of evolution, center on three key pillars: massive parallelism, radical energy efficiency, and unparalleled information density. Massive parallelism. Unlike conventional computers that process information sequentially, albeit with multiple cores, biocomputers are inherently parallel. A single test tube can contain trillions of individual DNA or protein molecules, each capable of acting as a tiny processor and performing a calculation simultaneously. This was the core principle demonstrated in Leonard Adleman's pioneering 1994 experiment, where he solved a complex routing problem by generating all possible paths at once in a soup of DNA strands. For problems that can be broken down into a vast number of independent, parallel tasks, known as NP-complete problems, this molecular parallelism offers a potential for speedups that are unattainable with silicon architectures. Energy efficiency. Perhaps the most compelling driver for biocomputing in the current era is its potential for extreme energy efficiency. The data centers that power modern AI and cloud computing consume a staggering and rapidly growing amount of global electricity. In stark path to radically lower manufacturing costs. 1.3. A comparative landscape. Biocomputing versus classical and quantum paradigms. To fully appreciate the role of biocomputing, it is essential to understand that it is not a direct competitor to classical or quantum computers, but rather a complementary paradigm with a distinct profile of strengths and weaknesses. The choice of computational technology depends entirely on the nature of the problem to be solved. A comparison across key characteristics reveals these distinct roles. Computational medium. Classical computers operate on electrical signals flowing through silicon circuits. Quantum computers harness the delicate and often fragile quantum states, like superposition and entanglement, of subatomic particles, requiring extreme cold and isolation. Biocomputers operate in a wet environment, using the complex biochemical reactions of molecules like DNA and proteins, or the electrochemical signaling of living cells, processing logic and speed. Classical computers excel at high speed, deterministic, and sequential calculations. A modern CPU performs billions of operations per second. Biocomputers, while massively parallel, are often much slower in terms of raw clock speed for any single operation. Their power comes from the sheer number of simultaneous operations. Quantum computers are not universally faster. They offer exponential speed-ups only for a specific class of algorithms, such as factoring large numbers, Shor's algorithm, or searching unstructured databases. Grover's algorithm. Problem domain suitability. One would not use a biocomputer to run a word processor or browse the internet. These are tasks for which silicon is perfectly optimized. The strengths of biocomputing lie in specialized domains. These include solving complex combinatorial and optimization problems where exploring a vast solution space in parallel is advantageous. Operating directly within biological environments for applications like in vivo diagnostics and therapeutics. Processing noisy and complex information in a manner similar to the brain, and applications where extreme data density and low energy archival are paramount. This comparative analysis leads to a crucial understanding. The development of biocomputing is not about trying to beat silicon at its own game. It is about creating an entirely new class of computational device tailored for the wet, noisy, and massively parallel world of biology, and for addressing the grand challenges of energy consumption and data density that are becoming the primary bottlenecks of the digital age. This represents a strategic diversification of our global computational toolkit. Just as we have CPUs for serial processing and GPUs for parallel graphics rendering, we may one day have BPUs, biological processing units, for interfacing with living systems or solving complex molecular problems. This is a paradigm shift from viewing computation as synonymous with electronics to understanding it as a fundamental and programmable property of organized matter in all its forms. 2. DNA computing. Programming the molecule of life. Among the various modalities of biocomputing, DNA computing stands as the most mature and well-established field. Born from a seminal 1994 experiment, it has evolved from a theoretical curiosity into a vibrant research area with tangible applications in ultra-dense data storage and highly sensitive molecular diagnostics. This section provides a deep dive into the foundational principles of DNA computing, explores its dual trajectories in data archiving and medical sensing, and details the latest frontiers, including the development of molecular neural networks and the transformative integration of nanopore-based decoding technologies. 2.1. Foundational principles. Logic gates. strand displacement, and self-assembly. The field of DNA computing was launched into the scientific mainstream by Leonard Adleman of the University of Southern California. In his groundbreaking 1994 experiment, Adleman used short, synthetic strands of DNA to solve a 7-point instance of the Hamiltonian path problem, a classic combinatorial challenge that is difficult for conventional computers to solve as the number of points, or cities, grows. He encoded each city and each possible path between them as a unique DNA sequence. By mixing these strands in a test tube, he allowed them to self-assemble through hybridization, forming all possible routes simultaneously, through a series of biochemical steps to filter out incorrect paths. He was left with only the strands representing the correct solution. This experiment was a powerful proof of concept, demonstrating that the massive parallelism of molecular interactions could be harnessed for computation. The power of DNA as a computational substrate stems from the exquisite specificity and programmability of Watson-Crick base pairing. Adenine, A, pairs with thymine, T, and guanine, G, pairs with cytosine, C. This predictable interaction allows scientists to design and synthesize DNA strands that will bind to each other in precise, predetermined ways, forming the basis for programmable molecular logic. Building on this principle, researchers have successfully replicated the fundamental components of electronic computers, logic gates, using DNA molecules. A variety of techniques have been developed to construct these molecular circuits. Toehold-mediated strand displacement, TMSD. This has become one of the most powerful and widely used techniques in DNA computing. In a TMSD reaction, an input single-stranded DNA molecule binds to a short, overhanging toehold sequence on a DNA duplex. This initial binding initiates a process where the input strand progressively displaces one of the strands in the duplex, releasing it as an output. This process is highly programmable and, crucially, cascadable. The released output strand can be designed to act as the input for a subsequent gate. This composability allows for the construction of large, complex circuits, including amplifiers, oscillators, and multi-gate systems capable of sophisticated logic, enzymatic and structural components. Beyond TMSD, other methods are also employed. DNazymes, which are DNA strands with catalytic activity, can be designed to cleave a substrate molecule only in the presence of a specific input, forming the basis for logic operations. Structural components like hairpin loops or molecular beacons can be engineered to undergo a conformational change, often resulting in a fluorescent signal when they bind to a target input molecule, providing a simple and visual readout for a computational event. Through these methods, scientists have moved beyond Adleman's initial experiment to create a robust toolbox for engineering complex computational behavior at the molecular level, setting the stage for practical applications. 2.2. The data revolution. DNA is an ultra-dense archival medium. While the computational capabilities of DNA are impressive, its most disruptive near-term application may lie in data storage. The global datasphere is expanding at an exponential rate, with estimates suggesting it will reach 175 zettabytes by 2025, placing an unsustainable strain on traditional storage media like hard drives and magnetic tape, which suffer from limited durability, security risks, and high maintenance costs. DNA offers a radical solution to this problem, driven by its two unparalleled physical properties: density and durability. Unmatched storage density. DNA is by a vast margin, the densest information storage medium known. Its theoretical storage capacity is estimated to be as high as 10 cab, 19 bits per cubic centimeter, or 455 exabytes per gram, a density that is 6 orders of magnitude greater than state-of-the-art magnetic tape. A single cubic centimeter of DNA could store more data than a trillion CDs, and the entire digital archive of humanity could be stored in a few kilograms of the material. This incredible compactness is a direct result of storing information at the molecular level. Exceptional durability. DNA is an inherently stable molecule, as evidenced by the successful sequencing of DNA from fossils that are tens of thousands of years old. Information encoded in DNA can be preserved for millennia with no energy input, provided it is protected from water and UV radiation. This makes it an ideal medium for long-term, cold archival of humanity's most valuable data, such as scientific records, cultural heritage, and government archives. The process of DNA data storage is conceptually straightforward. It involves two main phases: writing and reading. 1. Writing. Encoding and synthesis. Digital information, typically in binary format, 0s and 1s, is first converted into a DNA-based code using the 4 nucleotide bases, A, T, C, G. For example, 00 could be encoded as A, 01 as C, 10 as G, and 11 as T. Sophisticated algorithms are used to avoid sequences that are difficult to synthesize or sequence, such as long repeats of a single base. The resulting DNA sequences are then physically created using chemical DNA synthesis. 2. Reading. Sequencing and decoding. To retrieve the information, the DNA is sequenced using next-generation sequencing (NGS) technologies. The resulting sequence of A's, T's, C's, and G's is then converted back into the original binary data using the same code. This technology has rapidly progressed from small-scale demonstrations to the storage of significant datasets. In a major milestone, researchers successfully encoded and retrieved the entire English-language version of Wikipedia, approximately 16 gigabytes of text. In 2019, major technology companies, most notably Microsoft, have established significant research programs in this area, collaborating with biotechnology firms like Twist Bioscience to advance the technology. Despite this progress, two major hurdles remain for widespread adoption: the high cost and relatively slow speed of both DNA synthesis, writing, and sequencing. Reading. 2.3. Recent frontiers. Molecular neural networks and nanopore-based diagnostics. The evolution of DNA computing is now pushing beyond simple Boolean logic and passive data storage into more dynamic and sophisticated domains. Two of the most exciting recent frontiers are the development of DNA-based neural networks and their application in highly sensitive medical diagnostics, particularly using nanopore technology as a readout mechanism. Molecular neural networks, MoNNet, drawing inspiration from the successes of brain-inspired artificial neural networks, ANNs. Researchers are now constructing their molecular analogs using DNA, instead of rigid, binary logic gates. These DNA-based neural networks are designed to perform more complex, analog-style computations like pattern recognition and weighted decision-making. These networks are typically built using cascades of TMSD reactions, where the concentrations of different DNA strands represent the inputs and the weights of synaptic connections are encoded in the reaction rates or binding affinities of the molecular components. This approach offers several advantages over simple logic circuits, including greater compactness, scalability, and robustness against the inherent noise of molecular systems. A key goal is to create classifiers that can sense a complex pattern of multiple molecular inputs. For example, the relative concentrations of several different microRNAs, miRNAs, in a patient's blood, and integrate this information to produce a single, clear output, such as healthy or disease. This represents a significant step towards sophisticated, programmable molecular intelligence. Diagnostics with nanopore decoding. The most powerful application of these advanced DNA circuits is in the field of molecular diagnostics. A particularly promising target is the detection of miRNAs, which are short RNAs.